Hey, if you've ever tinkered with an electronics project, I bet you've come across this little guy, the LM7805. It's a voltage regulator, and seriously, it's everywhere. But have you ever stopped to wonder what's actually going on inside that little black package? Well, in this explainer, we're going to crack it open and see exactly what makes it tick. All right, let's get into it. So on the outside, it looks super simple, right? It's basically a black box with just 3 pins: input, ground, and output. And its job sounds simple too. It takes a higher, maybe kind of jumpy input voltage and turns it into a rock-steady, dependable 5-volt output. It's a simple gig, but it's absolutely crucial, which is why it's the go-to power solution for, well, countless circuits out there. But how does it actually do that? I mean, how does this little chip know what a perfect 5 volts even is? And maybe more importantly, how does it hold that voltage so steady, even if the input voltage wobbles or the circuit it's powering suddenly needs a lot more juice? What is the secret sauce inside? That's the big question we're here to answer. And to get that answer, we've got to go deeper. We are going to metaphorically pry the lid off this thing and take a look at its internal blueprint, the schematic. This is where you see the real magic, the real engineering genius. Okay, here it is. This is the schematic for the LM7805. Now, at first glance, it looks pretty complicated, right? A whole web of over 20 transistors, but don't let it scare you. It's actually an incredibly clever and, honestly, an elegant self-regulating system. Let's break it down into what it's really doing. Believe it or not, all of that complex-looking circuitry really just boils down to a closed-loop system made of 3 main functional blocks. Seriously, once you understand what each of these 3 parts does, the whole operation of the LM7805 is going to make perfect sense. To make this easy, let's use an analogy that I think works really well. Just think of the LM7805 as having an anchor, a set of brains, and some serious muscle. Each part has a very specific, very important job to do. So first up, we have the anchor. This is the chip's internal voltage reference. It's built with this really special circuit called a bandgap reference, which is designed to produce an extremely stable voltage. And I mean stable. It doesn't care about temperature changes, wobbly input voltage, or even how old the chip is. This is the unshakable standard, the golden ruler that everything else inside gets measured against. Next, you've got the brains, and that's the error amplifier. Think of this as the vigilant decision maker of the whole operation. Its entire purpose, 24/7, is to constantly compare 2 things: a little sample of the actual output voltage and that ultra-stable voltage from our anchor. If it sees even the tiniest little difference, what we call an error, between what the output is and what it should be, it immediately springs into action. And finally, we have the muscle. This is a big, powerful component called a pass transistor, and it sits right between the input voltage and the output pin. It takes orders directly from the brains, and it acts like a super precise, electronically controlled valve. You could also think of it as a variable resistor. This is the part that does the actual physical work of throttling the power flow to keep that output steady. Okay, so we've got our anchor, our brains, and our muscle. But the real beauty, the real elegance of this design is how they all work together in this constant, super fast, self-correcting loop. Understanding how this loop works is really the key to the whole thing. So here's how that feedback loop actually works. There's a pair of resistors inside that constantly samples the output voltage and feeds that sample to the brains, the error amplifier. So let's say the output tries to creep up, just a little bit above 5 volts. The amplifier sees this instantly because the sample is now higher than the anchor reference. So what does it do? It tells the muscle, the pass transistor, to ease up a bit. The transistor becomes more resistive, which drops more voltage across it, and that immediately pulls the output right back down to a perfect 5 volts. And of course, the exact opposite happens if the output dips too low. The amplifier senses it, tells the transistor to open the valve more, and boom, the output comes right back up. This whole correction cycle is happening thousands of times a second, which is how you get that rock-solid 5-volt output. This whole system is simple, it's robust, it's incredibly effective. I mean, there's a reason the 7805 has been so popular for decades. But this method of regulation does have a fundamental trade-off. There's an unavoidable cost for all this beautiful simplicity and stability. And that cost is heat, a lot of heat. Remember how the muscle, that pass transistor, acts like a resistor to drop the extra voltage? Well, that electrical energy doesn't just vanish into thin air. It gets converted directly into thermal energy, which is, heat. The math is pretty simple. You take the input voltage, subtract the output voltage, and multiply that by the current flowing through. That number is the power that's literally being burned off as waste heat. So if you're feeding it 12 volts to get 5 volts out, that 7-volt difference is just pure heat. And all that heat, it can be a really big deal. Just look at this graph. You can see that the chip's ability to handle power just plummets as it gets hotter. If you don't have a way to get rid of that heat, it can't handle much power at all before it just overheats and shuts itself down to stay safe. And that is why you almost always see these regulators bolted to a big piece of metal, a heatsink. It basically acts like a radiator for the chip, pulling all that waste heat away so it can do its job. So, there you have it. We've gone from a simple 3-pin black box to this really sophisticated, self-correcting system of an anchor, brains, and muscle, all working together in perfect harmony. It is a true masterpiece of engineering, all packed into this tiny, cheap little component. So the next time you see one, you'll know about the beautiful complexity that's hiding inside. The only question left is, what are you going to build with it?